So Professor Tushar Chaudhary is from MIT Pune, and he is one of our esteemed faculty partners of the Open Forum team of FOSSEE. So Professor Tushar Chaudhary will talk about a numerical simulation of convection-dominated flows using higher order schemes and their advantages.
Thank you, ma'am.
Yeah.
Mrs. Payal, ma'am. She is actually the backbone behind FOSSEE. So I thank for her effort, and thank you for the introduction. Very nice introduction. So I
Thank you,
am.
sir. It's our pleasure, actually.
So okay. So about me, I'll give a brief about me. How come I end up working on these areas? So I had done my PhD and postdoc from in aerospace engineering, particularly. And additionally, I was also a research scholar at IIT Indore. So there I worked on different numerical schemes, and my area was related to applied mathematics. So there I developed one scheme. So in this talk, I'm going to talk and show the results about that scheme and how that scheme was able to predict better than the existing schemes. So those all results are there. It's not very like a very innovative. I would say very novel, but yeah, slight modification we can get better result. It's not a very novel scheme, because if had it been very novel scheme, then it would have been used by all DCFDs. So, but yeah, slight novelties are there, and that has changed the result drastically, which I have presented in and published in the paper. Okay, so currently I'm working as an assistant professor in aerospace engineering department of MIT ADT University, which is in Pune. So MIT brand is around 40 years old now of Pune. So this is a sister institute of MIT, and it is in Loni Kalbur, Pune. So there I work on aerospace engineering related topics, and also since I have worked very profoundly on numerical schemes, so I keep on working in the development side of the schemes and the solvers. So some of the topics which I'll be covering during this presentation are: we'll see the introduction, how and where these schemes are applied, what all governing equations uh, we have in which we can apply these types of schemes, and we will also see an overview of different numerical methods that we have, and the shortcomings of those methods have given rise to a new class of scheme, that is high resolution scheme. Those schemes we will see, and I will also show you some of the comparison of the few numerical studies, and some case studies in my presentation, and how the results are better. So that's what is the plan of this presentation. Now, these numerical schemes that we often look for is the convective schemes or convection dominated flow schemes. The reason is because in case of convection, we if the since we are solving any numerical problem in a control volume, so the fluid property are going to flow very fast than the time constraint which you are setting for your computational domain. And so if my CFL, that is what we set in CFL number, right? So if my scheme, or if my convection, if the fluid is having very high speed, then my scheme, if I'm using lower order scheme, then although it will give the stability, but the accuracy, it will miss on the accuracy part. So that's why people often use these higher order schemes, but these higher order schemes are subjected to stability issue, and that's the whole point of this presentation. So how I'll show you how exactly these things do happen. So convection dominated flows refer to any fluid flow wherein we have convection or advection higher than the diffusion part. So generally, if you see the Navier-Stokes equation, we have inertia term, we have the convective force term, and additionally we have pressure gradient on the right hand side, and also we have the diffusive term, which is the viscous term on the right hand side. And if any external forces are present, then those also we do have on the right hand side. So in this whole Navier-Stokes equation, I'm just talked about a momentum equation. In this momentum equation, we have convection and diffusion. These are the major parts which are going to govern the flow properties. Okay, so in this, if the convection part becomes higher and the viscosity parts become lower, then we end up with such flows and which are uh, termed as convection dominated flow, and the ratio of these two, convection divided by diffusion, is known as the Peclet number. So Peclet number, if the Peclet number is very high, so high Peclet number flows, we see that convection is more uh, carried away more faster than the diffusion of the molecules. So some example of it, I have shown you the figures of some example wherein at supersonic speed, um, body is moving at supersonic speed, and on the right hand side we have the inlet of a, this is also a supersonic inlet chamber of an aircraft. So therein we have at very high speed the gases will be entering. Now in such scenario, what happens? The Peclet number becomes very high. And if I'm using some numerical scheme which are unstable, then my solution will not converge and it will diverge. So that is what we will see. Okay, so any Navier-Stokes equation. So for in Navier-Stokes equation, we have transport property. For example, let's consider the moment equation. So I can generalize my momentum equation using this form. So wherein I have just removed at this moment the time dependency, because we are not looking after the time based numerical scheme. We are trying to figure out the convective numerical scheme. So that's why I have ignored presently the time variable in this equation. So I end up with my set of equation which looks similar to this. The equation which I have shown, this equation is also known as the transport equation, a generalized form of transport equation. So wherein phi variable here represent any property, which it can be mass, it can be moment, it can be energy. So any property that we are going to assume that that is what phi represent here. So I can represent my set of equation in this generalized form. Now, if I take the ratio of the convective, which is the left hand side part, divided by the diffusive term, which is the right hand side part, I'll get the ratio term as Peclet number. And if this Peclet number is very high, then the transport of properties are going to be very faster. And if my scheme is not proper, then what will happen at the east phase? So here you can see there are denotation. One is P, W, P, and E, right? So these are the control volume grid points, P, W, and E. So P represent the central grid point at which we are presently there. E represent the downwind side of the grid point, and W refers to the upwind side of the control volume grid point. Okay. So if my Peclet number is very high, you can see at the bottom we have Peclet number is going to infinity. So in that case, what is happening? The dependency of the grid point, which is W, becomes lesser and lesser at the, if I am trying to find the fluxes. So at the fluxes, generally we use integral equation, right? So these are integral equations. So we will be having fluxes calculated at the east phase, west phase, right? So east phase, if you I am trying to calculate the fluxes at the east phase, you see here, due to the high Peclet number at the east face, I am having more dependence of W is coming on the east face. But if you see when the Peclet number was 0 on the east face, okay, what is east face here? So if these are the grid points, so in between there will, if I divide these grid point with a midpoint line, then that is the face. So for the grid point P and E, there is a midpoint line. If I draw that, then that is small e, which is the face point. So E east face, same way I can go for and calculate the west face, right? So that will be midpoint line of W and P. Okay, so for Peclet number 0, if I am trying to calculate for face, east face, so here I don't have any dependence of or any properties going to get changed with the W value. So W grid point will not going to affect the east face. So I will have whatever when the Peclet number is 0, I will have all the variation occurring only due to P grid point and E grid point. But if I go for high Peclet number, what is happening? At high Peclet number, I have dependency of even W grid point. Now, in this case, now if you see when the Peclet number is 0, in this case, I can use central difference scheme as well because Peclet number is 0. So if I take the central difference scheme for calculating east face, that will be average of the values present at P grid point and E grid point. So like that, I can calculate this. I can use the central difference scheme and calculate the east face value. But if I go for high Peclet number, I cannot use that central difference scheme because that central difference scheme will not give me information about the west face. So then we generally or numerically we generally go and explore the higher order schemes. Okay. Now there are different higher order schemes which you might be aware. So for example, quick scheme, this people often use. So there are different higher order schemes which are available, which have been devised way long back by different scientists. So, but now these schemes still have some limitation. Okay, so if I'm compare all these schemes, so first is the upwind scheme. Upwind scheme is the lowest order of scheme. Its order of accuracy is first order. First order. Then if I'm going to central difference scheme, it is second order scheme wherein I have the average. If I have to calculate each phase value, I have to take the average of grid points. Okay, so wherein we take the average. But when we are going for quick scheme will have the dependency for calculating phases, the dependency of all three grid points. So that is known and that was given to us by uh, BP Leonard. He presented his scheme, which is the quick scheme. But now, if I compare all this existing scheme, what can you see the result at the bottom? We have the solution oscillating. So we, when I'm trying to calculate, for example, if you are also trying to calculate Peclet number higher than certain value, for example, Peclet number infinity. If I'm going for Peclet number infinity, only scheme which will sustain or survive is the lowest, least order upwind scheme. Rest all, the central difference and quick scheme, they are going to get failed. So central difference will fail if your Peclet number is going more than 2, and quick scheme will fail if your Peclet number is going more than 8 by 3. So this is a scenario that we often end up on, and as we like as many people don't solve these high convective flows, so they don't need to bother. But if you are trying to solve such flows, then we often think that why the convergence is not happening. So these are the reasons, because oscillations gets into the solution or the when you are solving the Navier-Stokes equation, these solutions, these undue oscillations will eventually break your whole system of equation.
In the previous slide, what is 5 and the distance? Is that the distance between the centers?
No, phi is the variable I showed you in this equation. Phi can be mass, phi can be
Okay,
moment, phi can be energy. Okay, so phi is a
okay,
variable quantity.
okay. Mhm.
Okay,
And the distance is,
distances here I have not. Wait, let
and
me.
distance along diagonal. Mhm.
Yeah, this is adjacent. This is 1D case. So
Mhm.
it's on the horizontal, you can see the distance. But this is a 1D problem. I'm showing you a 1D
Yep.
problem. So
Distance between what?
distance between the this is for whole control, like whole domain.
The whole domain, or was it between the centers of the spheres that you
No,
showed in the
no,
previous?
no, no,
No,
no. The whole
no, this
domain.
is different.
Yeah, this is whole domain,
Whole
complete.
domain. Okay.
Okay. So if you see on the left hand side, we have the boundaries present, and on the right hand side again we have the boundary condition. So those are the boundary conditions, left hand side and right hand side.
So mean the two ends of the domain.
Yeah, yeah. So whole computation domain ends are one is at, for example, on the right hand side, we bottom we have one value at 100, which if I go see that value 100 is at the left hand side boundary, and right hand side 0 is the boundary condition.
Okay.
Okay.
Thank you.
So now what? Now, in order to overcome that, people have developed their many schemes, and those schemes are known as high resolution schemes. Okay, so those are the schemes which overcome the drawbacks of higher order schemes, which I just showed few. So, high resolution schemes which are there. These schemes, how it is different? These schemes, in case of some like these condition here, there is sudden sharp drop from 100 to 0. So in case of such condition, these schemes what it do, it try to jump from higher order scheme to lower order scheme. For example, I can have a high resolution scheme which is having quick scheme also present and few more schemes also present, additionally the lower order upwind. So in case of such condition occurring, like sudden drastic changes, it will jump to lower order scheme. So that's how people have devised different schemes. And these are snapshot of different schemes which are available in the literature. Okay, so I'll give you the reference of one paper so you can read later on. Okay, so now these schemes also we try to compare. So in my work, I try to compare these schemes and check the accuracy and oscillation. And generally, we always check for any numerical scheme the accuracy, the conservative property, the transportiveness property, and also the stability and convergence. So these are some classical test cases which people often use to test their numerical scheme. So first classical test here which I used is the step profile case, wherein at the boundary conditions are given. One is phi is equal to 1 and the another condition is phi is equal to 0. So if I have such a case, you see on the there is a diagonal separating these two conditions, transport condition, which are totally different. One is above the diagonal, all values are 1, and below the diagonal, all values are 0. Okay, and this angle I have set as 45 degrees. So if I take it's very easy to calculate the exact solution of this. This will be a exact perpendicular line. So, right. So this is how the exact analytical solution looks. And using this test problem, we what I did, we try to compare different numerical scheme and studied the how the behavior will be. So the lower least order upwind scheme is this UDS represent the upwind scheme, although it is the most stable, but it is if you see the capture of the profile, it is not even predicting the steep gradients. So that is what a drawback of these methods are. But rest all, if you see, more or less are somewhere closer. So if I need very high accurate solution, then I will either choose Cubista, Vaseb, or Hereg scheme, which is the last one. So then next test also I did was simulated the science per profile. Now why this was done? Because how it will predict, how the numerical scheme are going to predict the smooth curves. So if you see lower order scheme, they are not the upwind scheme. They are completely, if I draw one midpoint line and try to supermatch or superimpose these curves, the lower order schemes are totally off the symmetricity. So that's a drawback. So we, if generally for very convective, highly convective fluid flows, we should have a scheme which should also be symmetric in nature. So that will help improve the solution at the end. So, but rest, if you see the other scheme like Vasef, Cubista, and Hereg scheme, they show the capture of symmetricity. So those were the classical test of the which I conducted. Then the real test. Then we went for, this is also one classical problem only, but sometimes we usually we use this problem for testing the shock condition. And since this problem has the shock behavior as well, and it also have the expansion waves. So in this problem, we try to compare again the uh, schemes with the analytical solution, and what we found again here, the lower order schemes will not give proper solution, but the higher order schemes, if you see, they are uh, capturing more or less the similar solution. Now these were the old classical problems up to this last one, this problem which I showed you. This is a sword shock tube problem. Now real test case problem. So in this case, I try to study the real fluid cases. So this test case represent contraction 4:1 contraction channel. So wherein the outlet is one size and 4 times is the inlet, the channel width. Okay. So the fluid now here is allowed to enter is the viscoelastic fluid. Now such condition do occurs in industry, particularly industry people, they work with they often come across these viscoelastic fluids because of many of the industrial oils and the wax whatever we used, they represent this characteristics which is of viscoelastic fluid. Now, this fluid offers a very good test to the numerical scheme. And if I have lower order scheme, and if I'm trying to replicate my using lower order scheme, replicate the result of experiments, then all my numerical solution or whatever I try, whatever mesh refinement I do, my lower order schemes will not be able to match with the experimental result. So that is where people fails. So they need high resolution scheme, and people have done. So many people they use this numerical scheme so that their result come closer to the experiments. So next I'll show you. So how come? So this case UDS represent the lower order scheme. If you see here, I forgot to add one more figure of experiment. I should have added now. So that you get a better comparison. So in experiment, the experiment was showing the capture of two vortices. One is the lip vortex, which is present near the exit corner, which is known as the lip vortex, and the another one is the primary vortex. So this was the experimental result. But if you are going with lower order scheme like upwind scheme, this experimental result phenomena, you're never able to capture with whatever mesh you do. So that is where people use, or this is the application wherein the people go for a high resolution scheme. one of the application. So if you see here, I compared different schemes, and it was seen that Cubist and Reg scheme, they were actually closer to the experiment. Other scheme, so Smart and Vasev, I have shown here Smart scheme and Vasev scheme. These schemes actually failed to converge, and not just me. There were so a research group from Europe. They also proved that these schemes, both the schemes actually fail. Um, and so those schemes I tried in open form as well. So it got failed. So that is what like only schemes which provided results are these schemes which we got. And one more which was mean mode. So but the result and clam, but the results were similar to gamma. So I not plotted. So this was one of the application or proper application of high resolution scheme. Now another application you can further extend these high resolution scheme to another class of fluids, which is the compressible gas flows. So this domain you can see here is a forward facing step. So wherein the compressible gas is entering, and we have a wall present at the top. So at the top there is a wall present, and outflow, we set the outflow condition, and but wave transmittive condition, if you are using the open form, you should better be careful with that. So now this is the domain wherein the high compressible fluid is entering with a Mach number of around 3. So it's a supersonic flow. So the gas is entering at high Mach, which is 3, and it will come across one small obstacle, which is of 0.2 meter high. If you see, this obstacle is a sudden jerk in the fluid flow, so this will give rise to the oblique shock. So, and it will give like to oblique shock, which gets detached because we have a height. So this detached oblique shock we will see, and we try to capture using different numerical scheme. So if you see the results comparison of different schemes, we have here compared lower order upwind scheme, the gamma scheme, and I also try to put the result of smart scheme just to show how the convergence is affected. The smart scheme, since it is showing some oscillation in the capturing of the bow shock, so this takes a little bit more time to converge. We need special, in order to converge it, we need to tune with the special like some limiters, and also we need to put more restriction to relaxation factor if I want to converge this smart scale. So then I can make it converge, but it consumes a lot of time. So that's how, but the result uh, which I compared here, I have not used any extra relaxation factors to make the scheme converge. So those are the works with the same set of the relaxation factor and all condition for all numerical scheme. And if you see the results, we have a proper capture of the shock wave behavior. The oblique shock is this bow shock is properly captured. Then we have a reflection also properly captured from the walls. And so also, if you see, there are 33 contours which are present in this plot, but not all schemes are able to capture, except the few, which is the reg and smart scheme. So they were able to capture all those 33 contours, but rest all captured due to the lower order of accuracy, they captured lesser contours. So this was a brief how the high resolution scheme impact the numerical results. So this, if you want to see the or read the paper, So majority of results are taken from this paper. So this paper I have published in 2018, wherein I presented one scheme which is now known as EREC scheme. So I will be welcomed for any questions from the audience. And
Good afternoon, sir. There is this one question in the chat box.
yeah, please tell.
Yeah, the question is the HRX scheme available in open form?
No, I have not given to audience. Maybe in future I will definitely give to open form community, and if they include, maybe in their next version they will include.
Okay, sir. Thank you.
Sir, can you show the slide where you showed the name of the paper that you wrote on this topic?
Yeah, please wait.
Thank you.
Welcome.
Okay, so if there are no more questions for Professor Chaurashi, then maybe he can leave, and then Pranay can continue with the hands-on session.
Okay, thank you, Payal ma'am, for this.
Okay, sir. Thank you so much for your time, sir. Thanks a
Thank you,
lot.
ma'am.